All right, so in this part what I'm going to do is now I have my various half cells set up and I can read the voltage between two half cells. To do that, I'm going to use a voltmeter. A number will appear in units of millivolts when we connect these half cells together. The way the voltmeter works is I've got two different leads attached to the voltmeter, and then I will touch either of the metals to connect the two half cells and read a voltage. So we're going to start with copper and with zinc. When I touch them, you'll notice we're getting a number, and it's going to move a little bit. You're just going to pick one of the numbers and write down, but this is something on the order of 995 millivolts. If I were to switch these two leads and put the black lead on the copper and the red lead on the zinc, you're going to get a similar voltage, but you'll notice that the number is now a negative value. So right now I have right around negative 1,000 millivolts, which would be the same thing as negative 1 volt. I want to measure my half cell potentials referenced against the copper half cell. So what I'm going to do for each of the 6 measurements I'm going to make is I'm going to have the copper lead as the red lead and then the black lead going to each of the different half cells. So for my copper zinc electrochemical cell, I see a voltage of about 998 millivolts. So make sure you write that down and then convert it to volts by dividing by 1,000. For the next set of cells, I'm going to connect tin and copper. When I connect these together, I get a voltage of about 489 millivolts. Now this next one's a little bit trickier because I'm looking at iron as a nail. It's a relatively small nail, so I'm going to do my best to get good contact on this while still holding both of my hands in place. The iron half cell reaction, just give me a second. Just at a weird angle and trying to videotape. All right, the iron half reaction with the copper gives you a voltage of about 507 millivolts. I'm going to switch my hands around so you can see a little bit better. Now we're going to connect the copper with the lead. Got to find a good junction point on this lead. It's a little corroded. The copper with the lead has a voltage of about 436 millivolts. And then finally the copper with the magnesium. You see a much bigger number this time around. It's going to kind of jump all over the place. This is kind of an unreliable measure to make, but somewhere in the ballpark of 1690 millivolts would be a good representation of this reaction. All right, now you've got some math to do. So you're going to look at the voltage that we've measured. Excuse me. You're going to look at the voltage that you've measured for each combo of half cells, and knowing the voltage for the reduction of just the copper half cell, you can determine the voltage for the oxidation half cell, and then convert that oxidation half cell potential into a reduction half cell potential by switching the sign. Lastly, you're going to look up the standard reduction potentials for these 5 half reactions and see how your experimental data compares. In part 4, you will be comparing your observations from part 2 and part 3 to rank the different metals and the different cation solutions in terms of their strength as either reducing agents or oxidizing agents.